Today we will see the actual structure of our BJT and we will see the saturation mode operation in saturation mode. In the last class we have completed the active mode operation. Today we will see the saturation mode and the actual structure of the BJT. Let me draw that one. Okay. So this is the actual structure of our BJT transistor. It is a NPN transistor. There are two types of transistor. One is NPN and second one is PNP. Here where I have drawn the structure for an NPN transistor. These are nothing but the metal contact. If you remember the structure that we read before, this is for emitter, this is for base, this is for collector. These are the metal contact. Okay, that I have drawn here. This is from the cross view. If this is the my NPN transistor, if I will see it from this side, from this angle, this is the cross view. Okay, one point here, even my emitter, that is anti-material, and my collector, that is also anti-material, I can interchange this emitter and collector. Why? Because this NPN transistor is not symmetrical in structure. We will read in our MOSFET that the MOSFET is symmetrical in structure, so that we can exchange our source and drain. We will see in MOSFET that what is gate, what is source and what is drain, and we will see there that we can exchange our source and drain. As similar to emitter and collector, there are source and drain. As here is base is there, here gate is there. So here we can't exchange emitter and collector because of the non-symmetrical structure. But in MOSFET we can convert that one. Okay. One thing you notice, this is the base, this is emitter, this is collector. This is nothing but my collector base junction area, collector base junction. This is nothing but the emitter base junction. Okay, so you can observe my collector base junction area is larger than my emitter base junction area. Yes or no? This area is larger than this area, and we know that current in a semiconductor, that is the saturation current IS, that depend upon the AE. If you remember the formula, AE Q DN NP not like this. Okay, so my current that is directly proportional to the AE. It means as my area is larger, then the current in the emitter base junction diode, that diode is named as DC. Okay, here base is common, so for the name of collector I am written is DC. The current in DC will be larger than current in DE. What is DE? It is the diode for this emitter base junction. If this is one P N type, this is P type, this is N type. As this NP will combine, they will form a junction, PN junction diode. So that diode name is DE. And as this is DC, base and collector is nothing but DC. Here also one PN junction diode. So this diode name is DE. So current in both case is represented as IDC and IDE. Okay. So as the area is means collector base junction area, this area is larger than this area, my current in the DC will be much larger than DE. So in how much range? That is 10 to 100 times larger. Okay. So the current which is increased by this DE by 10 to 100 times of larger times increase than that diode current. So this is one diode whose value is DE. There it will be another diode, this value is DC. This is DC. So here the current will flow IDE, here IDC. So this current is larger. Okay, because of the area. Now we know what is in active mode. Our emitter base junction, that should be forward bias, and collector base junction, that should be reverse bias. So if I will exchange this emitter base junction and collector base junction with the biasing, then what will happen? If I will make my emitter base junction as reverse bias and collector base junction as forward bias, then what will happen? Then this mode of operation is called reverse active mode. Okay, we have learned three types of mode. One is active, second one is saturation, third one is cutoff. For all the three cases according to their biasing that we have to do. But here if you will exchange my emitter and collector, that is for biasing, that is emitter base junction will be forward bias, that is the This is why for active case, but if I am making here it is reverse bias, and the collector based on that is reverse bias in active case, here I am making forward bias, then what will happen? Then this condition is called reverse active mode. Okay, so here I will get one value of alpha and beta, that is the relation between IE, IC and IB. Similarly here I will get alpha, that is for reverse active mode, and I will get a beta, that is reverse active mode. For both cases I will get alpha and beta. Those values will be less than my normal alpha for forward active mode. Are you getting or not? This is for the normal active mode. This is for the reverse active mode by changing the biasing. So my alpha for this reverse active mode will be less than the alpha for this. Okay. So this is the cross sectional view, and these are some points that as my area is larger, my current will increase. Okay, and if I change, this is one point, but it does not have any practical application. No practical application. So we are not reading this one in more detail. Okay. Now let's see what is the saturation mode. So you know what in saturation mode, what are the conditions? My emitter base junction, that should be reverse bias. Sorry, that should be forward bias, and my collector base junction, that also should be forward bias. So this is the condition for my saturation region. Okay. Now tell me when a diode will become forward bias. If you remember the VI characteristic for a diode, what is the condition for the forward bias? This is the voltage, let's take this 0.4, and here is a value, let's take it, this is 0.8, here is 0.7, like this. So a diode, a PN junction diode will become forward bias if we will apply a voltage of minimum 0.4 volt to it, then only it will become forward bias. And till that value my current is 0, till that value means after 0.4 it will start conduct. Maybe it very minimal current, but after 0.4. So a diode will become forward bias if I will apply 0.4 volt across it. So if I draw the VCB versus IC relationship, what I will come to know? This is my IC, this is VCB. Okay, if you remember from previous active case, that our VCB, that is VC minus VB, that should be in for such active mode, that was in reverse bias condition. It means my collector, that is N-type material, that N-type was connected to positive voltage, and the P-type material, that is for base, that was connected to negative voltage. Then only it was becoming reverse bias. Now what I have to do? I have to make my collector base junction should be forward bias. Forward bias means this is N, this is P, this is N. So P will, how it will become forward bias? This P will connected to positive voltage, N will connected to the negative voltage. It means now it will become VC, VBC. It means VB minus VC. This is positive. Why I am writing VB first means it is because my base is connected to positive voltage. VC, it is coming later, means that C, collector, that is coming later, means it is connected to negative voltage. Similarly, you can see the VC, that is coming first. Why it was coming first? Because my collector, that was connected to positive voltage first, and this base is connected to negative voltage. That's why I was writing my VC first and VB later case. And now as I have to make this is forward bias, this VB, it will represent VBC, means VB minus VC. Okay. So when it will become forward bias, as I told just earlier, that 0.4 volt if I will apply, means my VBC value will equal to 0.4. What does in other way it mean? VCB value, which is nothing but minus 0.4. Okay. As my VBC value will be 0.4 or in more value than that, it means 0.4, 0.5, 0.6. It is meaning in that way. VBC equal to 0.4 or greater than equal to 0.4 means if my VBC, that is base is connected to positive, collector is connected to negative, that voltage applied is 0.4, 0.5, 0.6 volt, then only it will become forward bias. In reverse case, what I can say? My VCB, that is equal to minus 0.4 or minus 0.5 or minus 0.6. For that voltage it will become in forward bias, and if both are in forward bias, then it will enter in saturation region. So let me draw that one. This is the VCB axis, okay, which was before in active mode. You see, this was the active mode condition. It is the active mode. So from here, which point to which point it will become active mode? It was active mode till this point. But if you remember, even though if I apply 0.1 volt, then 0.1, 0.2, 0.3, for these values, up to 0.3999, till those values, my VBC will not become forward bias. Means for these values also, my BJT will be in active mode. In other way, what does it mean? My VCB value, which is nothing but minus 0.1, minus 0.2, minus 0.3 till minus 0.399, till this point also, means my active region will elongate from this point to move forward. Means for this case, my VCB is positive. Okay, we know if our VCB is positive, means VCB positive means collector is connected to positive terminal and base is connected to negative terminal. For that case, it is in reverse bias, and reverse bias means it is in active mode. Okay, it was the point for from here to the positive values VCB. Now for negative value of VCB also, for certain negative values of VCB, my BJT is also in active mode. What are those values? So these are the values, because even though I have applied a positive voltage to VBC, my diode, that is PN junction, is not on at this moment, because for on I have to apply a voltage of 0.4, then only my the PN junction diode will act, it will on, so it will conduct current. So before that value, this is nothing but the I versus V. It is no relation with this one. I am just explaining this, that till this value my current is 0, means till this value my that BJT is in active mode, still in active mode. Okay, so till the 0.4 volt my BJT is in active mode, and from 0.4 to any negative values it is in saturation mode. Okay, so if this is the VCB versus VIC. If I draw a graph between VBC and IC, you will get more clarity. Let me draw that one. You see, this is the current IC. It is now VBC. Okay. For this case, from here to here, my VBC is positive. From here to here, from here to till this towards the negative side, here VBC is negative. Okay. You see, for the negative value of VBC, negative VBC means positive VCB. This region is nothing but the same as this region. This is the positive VCB, which is same as negative VBC. So for this region, my diode is BJT is in active mode. Why? That collector base junction is in reverse bias till this point. Okay. So as it is in reverse bias, it is in active mode. Now I have increased my VBC 0.1, 0.2, 0.3, 0.4 like this. Okay. Even I have increased my VBC positive values, my diode is not on, because it need a voltage of 0.4 volt, then only on. So for this region also, it is also in active mode. It was in active mode for this case. So similarly you can check, this is for VBC 0 to 0.4. So if we will compare, this is VCB, which is 0 to 0.4 with a negative value. So for this value, it is also in active mode, and after that it is in saturation. After that it is in saturation. This graph, that VBC versus IC, is not there in your book. I just draw it for your explanation, for understanding that how changing VBC also it is not affecting the active mode. Okay. So remember, for VBC should be positive after 0.4, then only it will in saturation mode. After 0.4, from here to here, this region is saturation mode, and from 0.4 to onwards, before that it is in active mode. Okay. So we know in our active mode, our IC, that is independent of VCB. We learned this one before. IC is nothing but ISC e power VBE upon VT. Okay. So as long as my VCB is positive, all the electron they will swept to the collector side and the current IC will produce. So VCB has no application on IC for positive voltage. For positive voltage, for here to here in active mode, VCB has no application. Why? As long as VCB positive means collector is positive and base is connected to negative. So the electron they are in the junction, they will drop to the collector side. This is the collector base junction. So all the electron present over here, they will swept to the collector side and they will produce a current IC in this direction. Okay, so IC was independent. As long as this is positive, this VCB is positive, IC was conducting. But for this region, IC has an dependent on VCB. How? As this VCB value is less negative, this is VCB. As long as this VCB is negative, what will happen? My after certain value, that is for 0.4 volt, by applying VCB value 0.4 volt negative value, it will enter in saturation region. Before that it is in active region. In active region there is no implication. From here to the active region, my VCB has no implication on IC, means IC is independent of VCB. But for the saturation region, for this region, as long as my I have applied a voltage of minus 0.4 volt for VCB or plus 0.4 volt for BBC. Both are same. Here VB minus VC, here VC minus VB. As this voltage is applied, my BJT enter in saturation region. So in saturation region, my IC value fall, IC value decreased to 0. You see, this is the IC value. Here the IC value start falling. At a certain voltage, it will become 0. So for saturation region, my IC value decreases. Okay. If I show this one, how this IC value is decreases. If you remember the equivalent diagram, that 4 diagram A, B, C, D that I drawn for the large signal application. If you remember, this is nothing but my B means base. This is nothing but emitter. This is nothing but collector. This diode is nothing but DB. It is a current controlled, voltage controlled current source whose value is Is e power VBE upon Vt. Now in saturation region, as I said just before, as this collector base area is larger than emitter base area, this area, my current, that is Is across this collector base diode will be increased than Is than emitter base diode. So this collector base diode current increases, so that diode will act to reduce my current IC. That diode is named as DC. That is a collector diode, collector base junction diode. That diode will cause my IC value decreases. You see, this is my IC. When this DC was not there, this IC totally flowing. This IC, which is nothing but Is e power VBE upon Vt. This is the previous case when DC was not there. But as this DC came into picture, what will happen? Because of this DC, my collector current will decrease. This is the node. One current coming. This is one current. This is nothing but Isc e power VBC upon Vt. This is base. This is collector. So the voltage across this diode is nothing but VBC. And that will depend in terms of this current, which is nothing but Isc e power VBC upon Vt. So I can write my IC, which is nothing but minus this value, which is nothing but Isc e power VBC upon Vt. If I bring this term over here, what will happen? IC plus this value, which is nothing but the value Isc. To this node, two current are coming, one is going. That's why I have added two current. One is IC is coming, and the second current, that is this current is coming. So both are added at the left hand side, and right hand side only one current is leaving. So that's why I have written. Now what I did, I took this point to the left side, to the right side. Okay, then my equation become like this. So you see, when this term was not there, my IC value, let's take this is 10, and this is, let's take 2. When this 2 was not there, what is my IC? IC is nothing but 10. But because of this DC, my IC value reduced to 8. Okay, so here it is 10, now it is reducing. So as long as this VBC, which is nothing but VB minus VC, this voltage will increase. As long as this voltage will increase, E power value will increase. So the whole term will increase. And at some time it might become 10. Let's take any value of VBC that will give me a current 10. So 10 minus 10 will become a 0 for IC. So it is the value for which this VBC, my current is coming 0. Is it clear or not? So my this IC now depend upon VCB or VBC. Both are same. VBC and VCB both are same with a negative sign only. Okay. So my IC is now depend upon VBC. Before it was independent on VCB. Now it has some dependency. Okay. Okay, one more point. This IB, this is nothing but my IB. So before, when this term was not there, my IB is only because of this current. Okay, now my IB is increased. Whatever the current that was flowing through this diode plus this ISC e power VBC upon VT. What is the voltage? Which is nothing but VBE. Okay. So now my IC decreases and my I increases. By how much factor? By this factor. Before IB was the current that was flowing through this diode. Because of this DC addition, my IB increases to a value. What are the value before that? And it is added to a value ISC e power VBC upon VT. Now my IB value increases. So when for the active mode, my beta value, which is nothing but IC upon IB. What was the beta? Beta is nothing but my common emitter current gain. Common emitter current gain. That is the beta. Now for this saturation case, my beta is called beta forced. FORCED. That value is less than beta. That value is very less than beta. Why? You see, now my beta force, which is nothing but IC upon IB at saturation region. In active region, IC was high, IB was less in active region. In saturation region, my IC value decreases and my IB value increases in saturation region. So for saturation region, as this IC decreases and IB increases, so what will become the division IC upon IB? This value will decreases by beta. Okay. So for saturation region, my beta force is less than the for active region. This is the beta. So how we will come to know that our BJT is in saturation mode or not? There are two conditions. What are those? First condition is that my collector base junction that should be forward bias by 0.4 volt. Okay, that should be forward bias by 0.4 volt. It means my VCB should be less than or equal to 0.4 or VBC should be equal to 0.4, greater than equal to 0.4. Okay, it should be forward bias means base should be connected to positive terminal and the N side, which is nothing but my collector, that should be connected to negative terminal. That's why it came late. So either VCB that is less than 0.4 volt means this region, or the graph I did for VBC. This is VBC. This is IC. That value should be greater than 0.4. This is 0.4 line. So as this value will get greater than 0.4 or this value is less than 0.4. For that condition, my collector base junction will be in forward bias. What is the second condition that we read just? That our beta force should be less than our normal beta. Or indirectly, if I say my IB value will increase, my IC will decrease, then only my beta is becoming less. So this is the two condition for which my BJT will enter in saturation region. So in saturation region, what is the voltage across collector and emitter? This VCE saturation, which is nothing but VBE minus VBC. Okay, so this is the collector emitter voltage across the collector emitter voltage. You see, if I what I will write VB, which is nothing but VB minus VE minus this VBC means VB minus VC. Now open the bracket, VB minus VE minus VB plus VC. VB will cancel. It will remain VC minus VE. So this is the voltage VCE sat. What I will write in place of VCE? The first term will come first. The second term will come by second. That is VC minus VE, which is nothing but VC minus VE. So this is the saturation voltage across my BJT, that is for emitter and collector.